Welcome everyone to this first EDT seminar of 2026. It's great to have you all here, and we're super excited to have Lorenzo Cavallaro from our own group here. I guess he needs no real introduction, but
sure, you know.
But yeah, basically he's going to be talking to us about trustworthy AI for system security, and yeah, I guess
Thanks, Tristan. Yeah, thanks, Tristan. Hi everyone. So big responsibility in the first seminar after the year started. So I wanted to talk to you a little bit about our research visions and what we've been working on in my lab for the past years. And I wanted to use a buzzword, trustworthy AI, because I'm sure you might have heard about trustworthiness and AI, put them together. But I wanted to give a little bit of a spin. So the suspension marks are here not as a mistake, as more like as a cliffhanger. So trustworthy AI, but for system security. So there is a little bit of a different twist to it. So in particular for trustworthiness, we care about a whole different type of properties, fairness, ethics, depending on where you work in. But for us, when you look at system security and more particularly at software, we care a little bit more about other properties. So whether the system is robust, whether the system is explainable. And again, maybe these statements are ill-posed or a little bit ambiguous, because when you say robust with respect to what? What are the properties of robustness that you care about? So we'll try to actually advocate a little bit more down the line how the field has been shaping and what you could do, what are the opportunities, what are the challenges, and many more challenges, but a lot of opportunities as well. And maybe to set the scene, I just want to start off by saying that no days go by without reading about machine learning success stories, and I don't want to spend much time here, but I'm sure that you can agree with me, unless you not even been living under a rock, but you've been not on this planet. So you probably have heard about machine learning success stories in any walk of life. Predominantly, we had breakthroughs in computer visions and natural language processing tasks, but we've been using machine learning in a pervasive way in any walk of life, really. The question is, because I'm a security folk, and about security. So because we kind of seen a sort of revolution in machine learning when applied to computer vision tasks, natural language processing, recommendation systems, so forth, so on. In physics, in chemistry, I need not to remind you, but I wanted to do it because I wanted to boast on the UCL, so the recent Turing awardee and Nobel Prize winners. They had a stint at UCL. I'm talking about Geoffrey Hinton and Denisa Savitz, of course. And the question is, though, so about security. So it's just a new thing, because also in security now, AI security, everyone's very thrilled to say, it's very advantage, a lot of advancement and a lot of opportunities. Well, the truth is that we've been using machine learning security since the 80s. We haven't really called it AI. We probably haven't really called it machine learning back in the days. They were very simple statistical learning systems. Most of the times built on manually engineered feature spaces. So we wanted to solve a problem. We tried to characterize these problems in domain expertise. I say, okay, maybe to identify spam, I would care about specific keywords that would probably entice user to fall for it. And therefore, out of this, I would construct what is known as a feature space. So I would represent a complex data item, an email, for instance, in a numerical feature space. And I would use that to represent a spam email into a hyperdimensional space. And then I will try to learn, if the problem is a classification problem, try to learn a decision boundary between spam and ham messages. Okay. So the first thing that I want to mention to you about is the fact that I need to represent a complex object and as a numerical feature space. So this option, so this operation is known as a feature mapping function. This is a feature mapping problem. And in this feature mapping, some information is usually lost, right? Because you have a very complex text, and then you have to summarize it in a vector of numbers with some dimension. So for sure, you lose some information. But the question is, what type of information you lose? Maybe you retain still the original meaning of the object that is useful for you to carry out the task properly. And we've been using this, for a number of years on all different type of tasks. Whether it's about classification, whether it's about unsupervised learning, whether it's about identifying malicious software, or identifying vulnerabilities, or identifying spam from ham, network traffic anomaly detection, and so forth and so on. But when you look at papers published even until recently, probably 10 years ago, everyone was boasting very high numbers, like an F1 score, which is a way to quantified accuracy, very high, 99 F1 score, like, very, very high performance. So the question is, with that type of numbers, I would consider the problem to be solved and say, okay, we should be moving on to something else, right? And it turns out that actually problems are a little bit more complex than that. Why? Because security is primarily adversarial. So when you reason about security, you shouldn't avoid reasoning about adversaries that are trying to break your system, because those actually induce all sorts of different challenges and implications, especially when you deploy machine learning systems. So, and in particular, if you look under the hood at how machine learning works, what you see when you have adversaries in the loop, down the line, you observe a number of distribution shift from the original distribution you train your classifier with. So in a general term, so what you try to do when, of course, machine learning comes in different flavors, unsupervised, supervised, reinforcement learning, generative AI. Let's just focus on supervised learning, so classification tasks for the sake of simplicity, and focus on binary classification, so understanding whether something is good or bad. In principle, when you train a classifier, you use a training data set and you want to minimize the loss function. It tells you how good you are in your task. The only assumption that usually you do have is that data must be IIT. Now, how many of you guys have ever paid attention to this? Because when I was a student and in probability and statistic classes, every exercise started off, assume the data set is IIT, assume omega is IIT. I say, sure, but I'm assuming that, I'm all okay, I'm all cool about that. So I never really paid attention to the meaning of that. So the meaning is actually quite simple, but it bears important implications. So the assumption is that the training data set and the testing data set that I'm using should be drawn from the same underlying distribution probability. I usually don't know, I don't have access to, but they should be drawn from the same one. So the data should be identically distributed with respect to distribution. And there's another requirement that each sample should be independent from each other. You can relax that a little bit with exchangeability, but it doesn't really matter. So the important part is that IID is what governs everything. When you minimize the loss function of a classifier, or training a model, you're minimizing what is known as the expected risk minimization, or because you don't know the distribution, is empirical risk minimization. This is what you do. And that's the assumption is IID. So it's not clairvoyant abilities. The other requirement is that usually you operate in closed word settings. So if you have goodware, so if you have an apple and a pear, at test time, you shouldn't be seeing a banana. So you shouldn't be expecting to see another type of object, okay? Because that creates all different challenges in open word settings. So this is the only assumption that you reason. But if these assumptions is violated, then you observe different types of distribution shift. And why this assumption is violated? Mostly for two reasons. So one reason is that you see new knowledge. There's a new threat, there's new attack, something you haven't seen before in your training data set. And therefore, you do observe this distribution shift because you couldn't anticipate this. And that's usually fine. I mean, you need to deal with this eventually, but that's probably fine. The other distribution shift, though, that appears is a little bit more subtle, and probably we never really pay attention to it. The other distribution shift that appears is when the representation that you use to represent your data isn't precise. So before I mentioned you have a complex email, and you need to somehow compress this complex blob of information in a vector with different dimensions, where each dimension bears a meaning. If it's a manually engineered feature space, you give a meaning. It's like, this dimension refers to the presence of the or the absence of a specific keyword. If it's a learned representation, like with deep neural networks, for instance, it's a more opaque embedding. So it's the same thing, it's just a vector with numbers that has some meaning. But the point is that in this process, you lose a lot of information. And if you are not able to retain, I'm gonna throw a word here and don't get too itchy about it, semantics, and deal with semantics the way that you want to. You can be very formal and go down to formal method, or you can just treat semantics as intent. What is the intent of this email? What is the intent of this program? What is the intent of this network traffic, right? So if your representation is farther away to capturing semantics, what really matters about this piece of data, then your representation is brittle, meaning that too much information is lost. And two things that are different in a manifold in the real world can actually collapse in the same embedding space once you learn this representation, or could be represented in a farther away embedding space, even if they are very similar. You don't want to do this. Why? Because at training time, if I have similar things that are far away in the embedding space, I challenge the classifier to converge because I need to learn the decision boundary and I can't learn it. At test time, if I have two things that are similar but they're farther away in the embedding space, then I will make a mistake because once I learn the decision boundary, these 2 points should be the same or very similar, but they will have they are on the other side of the decision boundary. So one of them will be incorrectly classified. So this is very important because we don't pay too much attention to it, but representation are really key to the problem we're trying to solve. We don't pay too much attention about it because the mainstream ML, non-insecurity, is governed by natural language processing and computer vision. And for those tasks, we kind of have de facto standard accepted representation. So for computer vision, we had until a little while ago convolutional neural networks. And now we have vision transformer, and with natural language processing, we have transformer-based architectures that just compute condition probabilities over billions of particles. Okay, but we don't really think about much about it. In terms of other tasks, we don't have a de facto standard, right? So if I would ask you, how would you represent a piece of software? So you have a piece of software, binary, executable, macOS, Android, Windows. How would you represent that as a numerical feature space? Question I throw at you guys. Give me an answer. Any answer? Yes?
Graphically, like nodes and edges.
Say it again?
Graphically, like nodes and edges.
Nodes and edges. That's a good answer. What are these nodes and edges represent?
Data transfer between sample and component.
Cool.
Each node has programming group.
Yep. So basically, the answer is, I don't know if you guys heard it, but the answer is I can represent that my program as a graph where nodes represent data, for instance, and edges represent data relationship. This graph has a name. It's called data flow graph. So it captures exactly this property. You can have other type of graphs. For instance, control flow graph that captures control transferring of properties. You can have call graph that you look at a little bit more at a higher perspective between caller-callee relationships between functions. You can have a program dependency graph that combines control dependency graph and data flow graphs. You can have code property graphs where you have some other information where you include also the abstract syntax tree. So you can have all sorts of different graphs, but graphs are not the only one. So if you can use like a transformer-like sequence-based model, you just look at text and you build the condition probability of having, what is the likelihood of having that specific instruction, given that I observe these other instructions, and so forth and so on. And you can train masked language models of that. But the truth is that you can have even other forms of things. So there is no specific representation. And the point here is that what you really care about is about semantics. But again, semantics expressed in relation to the properties that you care about the data. If for you, the properties you care about is data flow relationships, then maybe a data dependency graph is the graph that you should be considering to represent your problem. And then now the question is, I have a graph, a very complex and big graph. How do I turn this into a vector of numbers? So until some years ago, you couldn't do much about it. So it was about capturing some statistical properties of the graph, like the in degrees and out degrees, some very simple statistics about instructions types or data types within each node, and so on and so on. Now we have graph neural networks, so we can learn embeddings. But graphs are big. Many of part of the graph might not be useful for the task. It's just there for the program to run properly. But you might be wanting to look for a specific signal across all this big graph. How do you do that? That's an open question. There are some approaches, but it's an open question. So what I wanted to basically tell you is just, I wanted to invite you to think about the representation, how you represent things. The way that you do it, there are different ways. I can't say whether one is correct or not. It's correct and wrong with respect to what you care about the data. But there are implications. There are definitely implications. You might end up with something that is more robust or less robust to distribution shift because you observe new knowledge or because you still get the old knowledge, but it's just represented in different ways. And at that point, you have the chance to meet. Okay, so what I'm arguing here is that we need to reason about improving the effectiveness of machine learning methods. for system security in the presence of adversaries. So we need to still understand that you have evolving threats, so there's a lot of distribution shift. You have adversaries that try to break the system, so there's a lot of adversarial drift, which is slightly different from a distribution shift, which is more naturally occurring, where adversarial drift is carefully crafted to break the system. And key to all of this is representation. So whenever you reason about this, you have to reason about how you represent your objects, how you represent your data, because that will create a large or a small or narrower semantic gap that will actually tighten up your classifier or loosen up a little bit more. And this has all sort of different implications in terms of performance on click data, robustness against this form of drifts, explainability of the model, cost induced, because to build a graph, it's a quite a computational intensive task. Keep in mind also that we mentioned about data flow relationship, but many of these relationships are complex to create on its own. So there's a lot of analysis that, so there's a lot of challenges in creating this graph, especially when you don't have, for instance, source code available. So there's a lot of indirect code, so you need to deal with. So there's a lot of uncertainty in the way that you build these graphs. So what is the cost induced by all of this? What is the final performance, and ultimately, how does all this impact on the trustworthiness of the AI pipeline for system security? So this is, oh, sorry, I thought that I had some stuff there, but I don't have it. Okay, that's fine. So to kind of, argue a bit more about this initial statement and this research vision that I outlined, I wanted to break down the conversation in three main pillars. And knowing myself that I keep on blabbing all the time, so I won't be able to finish all the pillars, so I'll be more than happy to share the slide with you guys if you're interested. And I'm in 169 first floor, so come in on anytime. So I wanted to break the conversation down in three different pillars. One is about adversarial drift, because I mentioned it's a type of drift. The other one is about natural drift. And the third one is about representations. So all the ingredients that we just mentioned, that all are important here. And in particular here, I wanted to talk to you about adversarial drift with a different angle, because you might have seen something that still stems from computer vision, because that's where the problem was brought up to the attention of the community as an adversarial attacks on images. But the problem is not related to images. The problem is pervasive across any domain where you use machine learning. Then I wanted to briefly touch on natural distribution shift and what you can do, because I mentioned that adversarial is still an open problem, but I wanted to show you some different formulation from computer vision. So what you need to be careful about whenever you deal with other domains. And it's still related to semantics here. So we will be using the word semantics quite a lot. So the second part is about natural drift. If you remember, the distribution shift can be caused by brittle representation, but also because evolving threats. So those evolving threats would lead to natural distribution shift. So what you can do here, I said that it's very hard to prevent this because you can't really foresee how the future would look like. So you need to deal with this. And there's a bunch of techniques from the ML community we can actually borrow and use it here. And the third one is understanding, okay, if we try to tighten up and learn some properties that we care about, do we have a better robustness to this drift or a better opportunity to explain attacks in a different way? Okay, so probably I will be able to talk about this, maybe skim over this. Unlikely I'll be able to reach here. If we're very unlucky, we'll be stuck here, okay? Which I suppose this is what's going to happen. But anyway, and for this, I wanted to tell you a story, okay? Because I believe stories are more interesting. And otherwise, starting on with formulas, I know everyone gets bored, and I get bored as well. So I wanted to tell you the intuition, and then we can drill down and look a bit more about the mathematical aspect. So for this story, I wanted you to open your mind and accept the fact that pandas are cute. And we live in a dystopic future. This is actually not intention. We live in a dystopic present actually nowadays. But so imagine something even more dystopian than that, where pandas are forbidden to roam around because they're too cute. That's the plot of the story. Okay. Now, the other part of the story is that people usually don't assume that because we see panda always chewing on bamboo stick, like, seems like, a bit lazy. Actually, not lazy. They are thinkers. So they are thinking, they're actually fluent in math. And they remember, and there was a paper that came out about 10 years ago, actually a bit more than 10 years ago. So this is a paper by Sejedi and et al., but there's another one by Battista Biggio et al. That kind of, highlights the same issues. So the panda remembers this paper saying, oh, I remember seeing something that if I can add some noise to an image, I can actually fool a classifier. So I could cause a misclassification of the classifier. Okay, interesting. So let me just try to understand, a little bit better what's going on here. So this is the image from the paper. So I believe you might have seen something like this. So this is the original image. The idea is actually you have an original image that represents a panda that is classified with specific confidence from the model. You add some noise, you end up with an adversarial example that is misclassified as a different class, gibbon, and with very high confidence. Now, this noise is not random noise. It's a carefully crafted noise that comes out from solving an optimization problem. The way that you craft this is actually you follow the same process through which you train your model. The only difference is that in training your model, when you minimize the loss function, you differentiate with respect to the weights because those are the ones that you want to change to minimize the loss. Here, you want to minimize this loss with respect to the input. You want to know what you need to change here so that you can create an adversarial examples that minimizes the loss with respect to the class that you want to misclassify this point to. Now, the formulation is a little bit, so you might, if you read about adversarial attack, you might see minimization of the loss or maximization of the loss, depending on whether the attack is targeted. So you want to misclassify the point as that point. So you minimize the error of being misclassified as this point, or maximization problem because you want to maximize the error that the point is classified as the ground truth. So I want to maximize the error that the point is classified as a panda. I don't care about what the point is misclassified to, but I want to maximize that error. It's the same thing, the dual of the other. But the point is that you build on the same backbone that you use to train models, with the difference that now the model is trained, weights are frozen, you just differentiate with respect to the input. You can do this because this is an end-to-end process, so you can differentiate the loss end-to-end. So this is what I mentioned. But the point is that we leave, oh yeah, this is what I just mentioned to you guys. Okay, so it's exactly the maximization. This is the loss function. This is you want to find the perturbation here that maximizes the loss function with respect to y. Y is the ground truth label, our panda. So I want to maximize this error. Usually you subject the perturbation to a sphere, to a small sphere of noise. Okay, and we'll get back to this point, okay, in a second. So you want to minimize with the sphere of a point because you're the panda. If you add too much crap, it's no longer a panda. You see, this is not a panda. Okay, so you want to minimize this noise. But I want to hold your thought on that, because this is usually how the problem has been formalized until now, until we published this work in 2020. So until 2020, because it stemmed from computer vision. So it makes sense in computer vision that you want to minimize the perturbation, otherwise the panda is no longer a panda. So you can see this from a minimization perspective. This is the empirical risk minimization. This is how you train your model. So it's exactly the same. But here you train with respect to the weight, here you train with respect to the perturbation. So the input changes you want to do. With respect to an LP norm, so this just tells you how you want to modify things, like you want to scatter or you want to have a certain intensity of changes in the pixel. But basically, it tells you how you modify things. And here you want to make sure that it's minimal. So you want to minimize the perturbation. Okay. Now, the point is that though we live in a real world, so this is cool when you look at images. I say, oh, I have an image, I want to add some noise, and then I feed it to a classifier, this is what happens, right? But the panda is in a real world. It's not in a computer. So the panda says, okay, I need to wear something. I need to go around and don't look at panda anymore. So the panda goes to a costume shop, but it couldn't find that noise. The noise exists in the digital world, in the feature space. It's so imperceptible that you can't realize it in the physical world. You can't print it out in the physical world, right? So, but it's okay because the panda says, I get the gist. So I need to settle for something that is close enough, like, approximate to that, kind of a projection of that noise. And then the panda says, okay, then the closest things to me is this wolf mask. So the panda wears the wolf mask, goes around. But unfortunately, there are still so many artifacts, so many constraints that are violated that give away the fact that the panda is a panda paws, panda belly, black and white fur, and so forth and so on. So, end result, panda is still banned from the city. So let's try to understand, what happened here. The ingredients is that you have to minimize or maximize. So there's to solve an optimization problem to find this perturbation. So far, the idea is that you need to minimize the perturbation because you want to reason about images. And if you have a larger perturbation, you're changing the visual perception of the adversarial example. So I wanted to twist this reasoning in a different way. Instead of minimizing perturbation, how about we try to make our statement based on semantics? So what essentially you want to do, you want to preserve semantics. You have a panda image, you add some noise, you have an adversarial image of a panda. What you want to preserve is the meaning of this image. If it was a panda before, to me, it should be looking still like a panda. To do this, I need to minimize the perturbation. I need that my noise has to be minimal, otherwise I give away the fact that there's not a panda anymore. If I want to do this attack on a road sign, I can't do this, perturbation. I can't print it out. But I can generate a sticker of a specific pattern or a specific color that I obtain by solving this optimization problem. And once it is stuck on this road sign, it misclassifies the road signs. Again, it's about the preservation of semantics. In certain cases, you want to minimize the perturbation. In other cases, you don't need to. You want your perturbation to be localized and shaped in a different form to preserve semantics. On code, it has no meaning to minimize the perturbation. What does it mean? Like, what do you care about minimizing perturbation? Whether you have 3 instructions or 10, who cares? You don't see it. It's a piece of executable code. You don't see if it's 3 or 5 or 100 more instructions. So what you want to do, you want to preserve the functionality. Because if it was a malware, after the adversarial attack, it wants this to be a malware. And this is basically the reformulation. And I wanted to kind of, go back to this a little bit better. So we have our image, we have X, which is the corresponding embedding, manually engineered, learned representation, doesn't matter. You have delta, which originally is obtained like this, but we don't, again, this is yet another way to formalize the adversarial attack as an attack proposed by Carlini and Wagner from UC Berkeley. But it's very similar to the formulation I showed you before. So in this case, you actually include the constraints in the minimization problem itself. So you want to minimize the perturbation. And this is the adversarial image. Now, when you reason about other domains, and then we'll see also that this is valid in computer vision as well, in natural language processing. So this formulation is a generalization of the formulation. But once you reason another domain, that formulation is ill-suited because it requires you to minimize the perturbation. But in certain cases, you can't. In other cases, you don't want to. So in this case, imagine that we have an application, a malware, classified as such. We have a corresponding feature space representation. So this is our representation. Again, it can be very brittle. So the semantic gap between these two can be very large, which means that the attacker has a lot of opportunity to move the way that you represent this object without changing its actual behavior. The tighter this gap is, the tighter the representation is to semantics, the less room the attacker has to modify it. Because if it modifies it, it breaks semantics. If it modifies it for its own meaning. Okay, so this is a very open problem. Like, we don't know how to do this effectively. Okay, so you find a perturbation, and the rest of the pipeline is the same. So, but again, in this case, you don't have necessarily to minimize the perturbation. What you care about, though, is about making sure that other constraints are satisfied. First, you want to identify how you can modify the objects, because in one case, it was about pixels in the image. And usually that comes because when you create the adversarial example, this is end-to-end differentiable. So the result of the operation tells you what pixel needs to be changed. But this is not necessarily differentiable end-to-end. So you have code, numbers in a vector. How do you go back to code? It's not straightforwardly designed in the process. So you might not have this is end-to-end differential. Does it preserve functionality? Is it plausible? So if I examine the piece of software, can I see that there's something dodgy there or not? Because again, security, there's no perfect systems about triaging things. And you know, if something is not, it's a security threat for the system, but it's no longer a threat. So for the model, it's no longer a threat for the system. It's not a threat. So is it plausible? Is it robust to some very lightweight analysis? And are there general constraints that can represent all of this? So, and there's also another part that I mentioned earlier, which is this inverse feature mapping problem that most of the times is not trivial to solve. So there's no generic procedures to do it. Even if you have a deep neural network that is end-to-end differentiable, sure, you can go back to the input space, but the input space is now not corresponding to instructions that might exist in the word. So I can tell you, okay, change this number into this other number, but you might not have an instruction that corresponds to that encoding. In a pixel, it's different. So you change the color, you change the alpha, you change some channel there. So it's slightly different. In text also is very much different because you need to have, you can always add some gibberish word, but if you want to preserve semantics, you would need to have a text that has a meaning, that preserves the meaning. Okay, so maybe to highlight the implications of this formulation, I wanted to have one slide. So if you forgot everything until now, just remember this slide. So here we have a fictional feature space, 2-dimension, so it's easy to represent. And here we have the red region is where you have bad points, malware, spam, you know, whatever you don't like. And on the blue region, you have good points, goodware, whatever you like. And you don't see it here, but somewhere there is a decision boundary that was learned by the classifier, and the arrows identify the direction of the gradients towards the highest change you need to make to move a point from the malware area to the goodware area. So the attack wants to take something that is here, add this perturbation that we mentioned, and move it here, okay, across the boundary. So there is some boundary here. Now, within this region, though, you can already identify what we called a feasibility space. Sorry, I forgot. I've been giving this too many times, but I forgot. Feasibility. Oh, it's written there. Feature space feasibility region. Because it exists in the feature space. And this region is a region where all the points in your data set have a corresponding representation. You could have other points here because those are the possible values of those two features, but you don't have it in your data set. So there's some uncertainty here because you don't have enough data. But that's fine. So you can identify this area. Actually, you can identify, I should be more precise, this area exists, but you don't know the shape of it. Within this area, also you can identify problems, what we call problem space feasibility regions. So these problem space feasibility regions are regions that corresponds, whose representation corresponds to real programs that performs the actions that are malicious or benign. So here you might have other programs, but they might not compile, they might crash, they might not actually be completely malicious. So they exist in the feature space, so you have a corresponding representation, but you might not have it in the real world. So the idea now, the attack is that you start off with a point in the problem space feasibility region. Why? Because you start off with a real model, a real piece of code. You learn a representation. So this will have here. You solve one of these optimization problems that we just mentioned. FGSN, PGD, AutoPGD, Carly and Wagner, doesn't matter, but think about this formulation of optimization we just mentioned. And the idea is actually, as you identify features that you need to add or how to change the program to induce changes in the embedding that you learn, the idea is actually you move the point somehow across the boundary towards the region of benign points. Now, this is good. So this already breaks the classifier, okay? Because you give this vector to the classifier now classifies this vector as good. The point is that the real life doesn't work on vectors. Real life works with programs. So you need to be effective. You need to have, from this vector, you need to create a program that runs and preserve the original malicious functionality. Otherwise, the problem with numbers. matrix computation. It's a problem with the model, but it's not a threat. I don't have a corresponding real program. I don't have a corresponding real threat. So what I need to make sure is that I can satisfy the constraints that we mentioned earlier, so that this point is projected somehow by satisfying this constraint into one of these pockets, in this problem space feasibility pockets. Now, I don't know how many of them I have. I don't know where they are, but I know that by solving those constraints, I somehow project the points back to them, because I then can create a real piece of code that breaks the classifier, but also affect the system. So I can run it and can infect the system. And in this process, the interesting thing is that you start having another term that appears. So delta is our perturbation, the one you need to add for the attack to be successful. Now, we also have another element here, it's called eta. So this term appears because you want the attack to be realistic, you want the attack to be real. Now, it could be in the form of additional dimensions, if you have a manual engineered feature space, for instance, or it could be in changes in the embeddings, if it's a learned representation. It doesn't really matter. It just affects the way that you represent the problem. And by affecting the way that you represent the problem, your attack might actually be more or less effective, because I was able to push the point here. Now, if I project the point, and by satisfying constraints, I might project the point back here, which is much closer to the boundary region. So my attack success rate might actually have decreased from the original one, but it's a realistic one. Okay. And the question also that I want to throw here is, how can I use all of this for defenses? Can I use, this is just an attack, but can I use this for defenses? What is the implication for defenses? TLDR, because we won't be able to get there. It's an open problem. So there's some progress, but it's an open problem because there are so many variables. Representation is one of them. The ratio of malicious software you need to use, the type of attack you use, the model that you have, how is the decision boundary, is it smooth, it is very pointy. So there are so many variables that we don't know whether there is a definitive answer yet. Okay, so, and this is basically how the problem should be reformulated up. So you can read more about this into our work we published a few years ago. So this is the original, one of the original formulations. They're all equivalent, but just one of the original formulation. This is how we reformulate the problem. Now, it looks very complex, but it is not really complex. Like, you know, the first part here is about transformation. So how you change the object that you care about. You can add some code, you can remove some code, you can modify some parameters, you can add some parameters, and so on. And of course, you know, if you work on images, it's the same thing. You can add a pixel, so, or, you know, change the value of a pixel, or modify the value of a pixel. So it's the same thing. This one is probably the most important one. So this is about preservation of semantics. Now, semantics equivalency is undecidable in computer science. So if I ask you that you need to create something that's semantic equivalent, I will be lying to you or be asking for something impossible. But what it is important is the superscript here, tau. So you want preserved semantics, not for the whole code, one-to-one, only with respect to some specific actions that you care about, this tau here. So the original program should, and the transform program should have the same semantics with respect to tau, the functionality you care about. Meaning, if the malware contact a command and control server, and the adversarial malware should still contact the command and control server. If the malware deletes a file, then the adversarial malware should still delete that file. Now, all the rest, I don't care. I don't want that all the other semantics are preserved, as long as they don't interfere with the functionality of the malware. So I want this to be plausible. So when you look at the malware, you shouldn't see that you see a bunch of instructions that say they're clearly disconnected from the data flow, for instance, or the control flow of the original program. So I want to have something that mingled into it. And it should be robust to preprocessing. So these are very high level constraints that, of course, you need to instantiate depending on the domain that you care about. The way that you find this, you can find different search strategy. You can have a gradient-driven attack, like the one I showed before. You can modify the problem space, so the object, and see how this is reflected in the embedding space, or you can have a hybrid solution. Very high level, more detailed in the paper. Okay, I wanted to show you maybe very quickly some numbers, some implications. Okay, this is a theoretical formulation, but you know what's going on. So now we ran this experiment on Android not because we particularly care about it, because there's an abundance of data, so we can actually have a thorough and sound experimentation around it. So here we have an Android malware that goes to a doctor and say, you know, I also made careful to be considerate, so you have you have a malware, so, I want to go to a doctor, so, doctor, I'm a bad guy, but I want to be this guy as a good guy. Say, no problem, I can take care of that. And to do this, we actually used, to make sure that we satisfy functionalities, we actually looked at a corpus of benign software. We harvested some good functionality from this benign software, and we transplanted into the malware, similar to organ transplantation. So we follow a technique that's known as software transplantation, which was created here at UCL. I guess Earl Barr was an author of the paper. It was very cool, and we haven't used it here because yes, we're buddies, and no, I was still at King's there, so we didn't. Oh, we knew each other, but I was not trying to please him. So the technique was actually very cool. So we did the same. So we look at the corpus of benign software, we identify the functionality we care about, technically we take what is known as a slice, a program analysis slice. So we don't just select the specific feature we care about, but we select the feature along with code and data that is connected to that feature. We take and we implant it into the original software. Now, to make sure that things don't interfere at runtime, we guard this software transplantation with an opaque predicate, which is a guard condition that resolves to either true or false, but it's hard statically to identify whether it's true or false. So in our case, it was false because we didn't want the code to execute, but we wanted the analyzer to actually see the manifestation of this. Okay, let me just fast forward. Let me just look at some numbers. Okay. So we looked at a large data set, 170,000 apps, 10% malware from this time frame. There is a reason why it's a 10%. It's in another paper of ours. I can share details another time. So we looked at two state-of-the-art models at that time. Draven, which is a very, very simple manual engineered feature space where each dimension represents an API that might be in the program or not. It's a bit more complex than that. So there are also URLs and strings and stuff, but just to give you the gist. So it's very simple, binary encoded feature space. Okay, you lose a lot of information because I say there's an API that might get executed or not, and I don't know anything else about the program. So I don't know if there's data flow relationship. I don't know whether the API will be executed or not. But it's a way to represent the program. So I represent a complex object in a hyperdimensional space. The representation is very brittle, so it means you can change 1 and 0 at your will without affecting the functionality. Linear SVM, so a very, very simple linear model, which is useful to crafting the attack because you need to solve this optimization problem. But if you have a linear model, you know exactly what are the features that contribute the most to a benign classification. You can rank the weights, and then you select whatever feature you care about. Because also the feature space is explainable, it's interpretable. I know that that dimension corresponds exactly to that API, and I have the weight that tells me how these two are connected. SecSVM is another model, which is the same of Draven, but it has actually a hardened model that was hardened with respect to adversarial attacks. The idea is, so SVM relies on a few top features to make a decision. Yeah, so there's a very long tail, but there are a few top features to make a decision. Now, SecSVM was designed in such a way to clamp the weight in the training process so that it forced the model to use more weights. Now, why this? Because the assumption until then is that you had to minimize the perturbation, meaning you had to minimize the number of features that you could use in the attack. But if I force you to use more features, then of course the attacker is limited. That I have a model that is hardened. But we don't have that constraint because we can use as many features as we want. There is some other constraint we need to take care of. But what I wanted to show you is not the fact that we break the model. That's unsurprising. What I wanted to show you is how fast this curve grows. And you can see that we can have a 100% attack success rate with about 110, 120 features, including the original features, not just the side effect features or the attack features, so the whole features. You might argue, is this a lot or a little? I have no idea. Well, this is out of about 10,000 feature space after feature selection. So before this, it was millions, but after feature selection, we're about 10,000. So it's really like a drop or a needle in a haystack. And the different settings of the curves that they represent how far we want to go into the region of benign points. So we want to just cross the boundary, or we want to go a bit further down towards the region of dead spot. And I want you to reflect on this as well, because if I'm able to push my adversarial example in a region where it's dense of benign points by preserving functionalities, it means that the representation I'm using is very brittle, is very imprecise, because in real life, if I'm able to do this, you can always do that because you exchange numbers. But you have a robust representation, it means that you lose functionalities because there you wouldn't have points that have that semantics. So if you're able to do this, to move the points there and still satisfy semantics, it means that the representation it loses too much information. You have to go back and design a new representation. Okay, so the question is, how does this affect problem space constraints? Because we said that we don't care about perturbation, but of course, if you create adversarial examples that are 1 gigabyte in size, you're giving away something that is dodgy, right? So we compute the statistics across different properties, you know, size of the adversarial examples, the average schematic complexity, permissions, API calls. These are all specific to Android, but all features that you care about. And turns out that actually the distribution of our adversarial example is always within the mean plus minus 3 times standard deviation from distribution of the benign corpus. So you can't really see that something dodgy has happened here. So the question is, okay, you did it on Android, but you mentioned that this is quite a generic formulation. So in the paper, we have some other arguments about this. But other research groups picked up on our formulations and started, now looking at the problem. So not just on Android. And here, this is a problem that's absolutely completely different. So not on code, text. In particular, these guys. So this is Conrad Rick that was a Braunschweig before, now is at TU Berlin. They relied on our new formulation to create adversarial examples of research papers. So the thing here is not even fictional, and I'll tell you why it's not fictional. So there are, in general, when you bid for it depends on the conference systems. But in general, for security at least, we use a system. Most of the time, it's called hot crap. It's called hot CRP. But we call it hot crap. It's not crap, by the way. It's actually very nice. And it's very good. The way it works is that you have to bid on the papers that you wanted to review. Now, because we started seeing increasing numbers, like in the thousands, it's a very tedious process. So now what we started using, so this was piloted actually 10 years ago, but now this instance of CCS, which is one of the top conferences in security, uses the same model, which is a model developed by University of Toronto, which models the problem as a topic labeling problem. So ideally, you as a reviewer submit to the system 10 or so papers that represent your expertise. The system builds profile of that expertise. And when you have a new paper that is submitted, then the system tries to understand the topic of that paper and then assign it to a reviewer for review. So it just helps to this bidding process, to automate this bidding process. And also there's a colluding ring issues that we're facing in the community. So also it should ameliorate that. But you can create adversarial examples. So you can modify the paper in such a way that the paper is assigned or not to a specific reviewer. And this is by leveraging the same reasoning that I just mentioned earlier. Here is important because you have the no inverse feature mapping problem. So you have an embedding. From this embedding, you have to go back to text. And the text has to be meaningful. It's not just the symbols. Like it has to be meaningful as a text. So it's possible to do this attack, and it worked, and it relies on this new formulation. But there are a bunch of others. So we tried this so we published in Oakland 2023 on backdoor attacks. So not evasive attack, but still adversarial attacks at training time. We use this to harden our classifier in reinforcement learning on dynamically executed traces. We also try to explore the robustness of binary function similarity systems, which are a cornerstone of many security tasks. So imagine if you want to find vulnerabilities for which you have a specific pattern. The idea is actually you want to learn a representation of that specific vulnerability, and you want to search for it. So this is a query function. You want to look whether you have similar code that exhibit a similar pattern. Now, of course, the role of representation here is fundamental because if it's too far from the semantics, you don't really catch anything that is semantically equivalent or close by. But there was a work a few years ago that actually tried to benchmark the state of the art at that time that was evaluated on slightly different benchmarking data sets. And it turns out that actually most of the approaches had the same performance once you normalize experimental variables. So with this work, we try to actually explore the other dimension. So again, it's no longer enough to say F1 score, I have the highest one and I'm the winner. No, no, there are a bunch of other questions that you need to start reasoning about. Are you robust to adversarial attack? Are you robust to natural drift? Can your model support explainability? What is the cost associated to that? So all of these are interesting questions, and sometimes there's a tension. In fact, it turns out that with this work, we found out that the models that were sometimes down-performing the state of the art were the one actually more robust. So which one you're going to use, it depends on your threat model. So adversarial attacks, of course, I spoke about code, but of course, there are also things in real life. So in this work, there was CCS 2016. They tried to create accessories that once they were worn, you could actually misclassify people going around. And I believe, this is Lou Robert, so one of the professor of the study, and I believe that he was also misclassifying Milan, which is pretty cool. There's also, I guess, in the latest was Mission Impossible, I believe, without doing any spoiler, where you had this AI gone rogue, which is a plot nowadays is very easy to build upon, where there was a certain point that there was the villain going around, and I guess Tom Cruise has the Meta glasses, like the Ray-Ban fancy glasses, and he saw somebody in the screen, and then this somebody disappeared because the AI canceled it out, right? So in a sense, it's the same thing. So it was an adversarial. This is not sci-fi. This is adversarial attack. You can do it. You can actually, there are papers that shows cloacal invisibility on digital videos where you wear it. It's just, you just are canceled out without using green screen, of course, because you can use green screen. Okay, so you can do something on natural language processing, so natural text. So this is a work which is very similar in flavor to our own work, but instantiated from a natural language perspective. That was published a few years ago at AAAI and Oxford. So you can see that the problem reformulation allows for sort of a very interesting conversation you can have around this. So it's not just a single community problem, it's a cross-community problem. It's not just an academic exercise, though. And as promised, so I'm going to steal you really drunk, like 2 more minutes, 2 more minutes or 3 more minutes. And as I promised, we won't start on this. But what I wanted to tell also is that this is not an academic exercise. So a few years ago, in 2019, there was a company, Silence, that went on the market with their anti-malware system, arguing that their anti-malware system was the coolest because they could rely on representation learning, and they had a system that learned representation. You didn't have to manually engineer anything, and the system detect malware. It was the best in the world. Turns out that some folks decided to look at the system and then create adversarial examples. Now the system relied on a very simple, not very simple, very obvious representation that was brittle. So it was not hinging much on semantics. So you could actually add a lot of code at the end of the sections or stuff like that to actually steer the model in its own classification. So they broke the system, but there's a very interesting positive twist to the story, because the guys, they didn't go away and lick their wounds. They actually resolved themselves, so to say, oh, we saw firsthand the perils of adversarial attacks on our own systems, and they want to found a company. It's called Hidden Layers, which has raised 50 million last year or 2 years ago. I don't have any stake in the company. Just one of my students is working there after his PhD, so we have good relationship with them if you want to follow up on this. So before leaving you guys, I wanted to, so I spoke about attacks, but the real meeting was about telling you to focus on semantics, representation, knowing that there are all these issues and implications. So the question is not really about the attack per se, which is important because you want to know how your system is robust against real attacks, not feature space attacks. The question is, can I use these attacks for defenses? Now, when it comes about defenses against adversarial attacks, there are essentially 3 directions. So one is abstention. So you design a classifier with a rejection option. So if the classifier is very uncertain about it, so, I don't know, and then something else needs to happen. The other option is certified models, which you provide guarantees that the classification of the model doesn't change within a specific epsilon sphere bounded perturbation. Okay. The third one is about robustness. And you want to create a model that is robust with respect to some of these attacks. And an obvious technique that was proposed right after the attack surfaced is adversarial training. As the name suggests, it's very simple. As you train your model, you also, so your model, the training of the model is a minimization optimization, right? The minimization, the empirical risk minimization. Now, you also add an inner maximization problem, which requires you to create adversarial examples, okay? So as you train your model, you use training points and adversarial points that are generated depending on the strategy on the fly offline. And you want to create now a boundary that accounts for this perturbation. Now, the problem is that the approach would work if you could enumerate all the points in your data set, and if the representation would be quite tight, very non-brittle. The problem is that sometimes you're working continuous values, so you have infinite points, so you can't really do it. And you're affected by the specificity of the attack. So how you create a point. So I showed you like conceptually how the point moves across the embeddings, but depending on the attack you use, of course, the point moves slightly differently. So in general, you obtain with adversarial attack, an empirical protection with respect to a specific set of attacks and perturbations. But the question is, should I use feature space attacks or problem space attacks? Because if you remember the slide that I asked not to forget, in principle, what I should care about are the problem space pockets, because those are the one that corresponds to real attacks. But the question is more nuanced than that. So the answer is more nuanced than that. And it's unclear. So sometimes it seems that feature space are better than problem space. Some other times problem space. And we're trying to understand what are the properties that will help us in the future, given a model and representation, to understand which one should be working better than others. There is a specific reason for asking this, because it's very cheap to create feature space attack. It's very complex to create problem space. The inverse feature mapping. Okay, let me just skip on adversarial training, which I mentioned now. So there is preliminary work that explored this on, so published at SMP in 2023, that explored this across different tasks. Text classification, not Gen AI. Text classification is sentiment analysis, so old-fashioned stuff. Botnet traffic and Windows malware classification. So they fixed models, they fixed attacks, they fixed representation. So they took some state-of-the-art there. And what they found out is that, and they benchmarked problem space versus feature space attacks. What they found out is that both for text classification, so sentiment analysis, using problem space attack marginally helps more than feature space attacks in adversarial training. In botnet traffic hardening, not required. In Windows malware, it is actually required. So the challenge is quite staggering. So it seems that this is a task-dependent result. The truth is that when we try to run these experiments on our own examples that I showed earlier, well, you see that, so it's a bit complex, but just look at these two columns and increasing budget of perturbation. Again, you don't have to minimize, but it's very hard to reason without bounds. So we just have an increasing budget of perturbation. And here you see that if you use problem space adversarial examples in adversarial training, you lower the attack success rate much more than using feature space attacks. Of course, you test only using realistic attacks. But if you use, this is even more evident if you do this on SecSVM. You remember the classifier that climbs the weights and uses more features? Why? Because it has to use more features, so the space of exploration is more complex. So in feature space, it's unlikely that you are going into a problem space region. So it's more likely that you focus on regions that you shouldn't have focused on. So you tight the model on something that doesn't matter. So again, this opens up, this tells this not a task specific, it's something more nuanced with the model. So there are now tons of questions that you can ask yourself, whether it's the abstraction, is the representation, is the model, is the attack, is the decision boundary smoothness, is the ratio of adversarial attacks, and so forth and so on. So we try to reason about this with this work, and more to come. So I'll tell you in a second. Okay, as promised, we would have just gone here, so no time to go here. So I'll go fast forward to the end. See, I was very, very, very optimistic. I'm always optimistic, but so this is what I mentioned at the very beginning, right? So I said, okay, security is adversarial, so I feel that you need to reason about adversaries. You need to reason about representation because in many domains there's no standard representation, and how this impact the rest of the pipeline. But because there's no standard representation, actually, I want to reformulate this a little bit. So I had a little bit of time to think about it, and so I wanted to reformulate this. So maybe it's not about just thinking about representation on their own, because I don't believe there is going to be one representation that wins. I believe there's going to be now a hierarchy or a plethora of representation. It needs to be orchestrated somehow. And the idea is actually what I really argue here is that we should try to work on the science of governing representation for trusted code reasoning. So hierarchical representations that are governed by uncertainty. I could talk about uncertainty, but it's very important. So if you don't know something, you abstain, and then maybe you use another representation that captures different properties until you get down to the pipeline. And semantics grounded AI for secure and adaptive systems. So this is all buzzword, but semantic ground is very important because one part of the representation I wanted to talk about is about LLMs. So these models needs to be grounded. And the more you can ground them with semantics, the better it is. So there's a lot of interesting opportunity here. And I believe this hierarchy is very interesting. So we worked a little bit on representations and semantics grounding. We worked a little bit on uncertainty quantification on non-LLMs. We're expanding now to add this notion to LLMs. We're not the only one. So it's a vision. So it's a community problem. So it's not just one paper. And also, we are interested in understanding how this steer and enables LLMs and agentic AI to solve these problems in a more comprehensive perspective. So on this part here, I believe there is something on problem semantics for vulnerability. So these are also something we're piloting in a startup that we co-founded. And we found 7 0-days vulnerability for Android, so on, for Apple in the Apple ecosystem, so on binary code. And yeah, I guess, this is not everything I wanted to tell you, but a good portion of what I wanted to tell you. Okay, thank you. Questions? I'm not disappearing. I work here, so enough. Yes.
Thank you so much. Super interesting. I was just wondering around like what you called natural drift.
Yeah.
You have adversarial drift, and if there's a lot of research like in the combination of those.
There's no lot of research in a combination of those because they are hard on their own.
Yeah.
So there is a natural interest to conceal them both, but we don't have bulletproof solutions for neither of them. Mm-hmm. So combining them together is challenging. And this is also a message that I wanted to send. So we had a paper, this one on. So there's a work that we're doing there to learn temporal invariance. So features that are invariant across time, because usually drift, we observe drift as a consequence of time-dependent evolution. And I believe it's an interesting approach. So we sent to security conferences. Security conferences are adversarial by nature. And the main critiques is that, but you're not looking at adversarial attacks. So reject. So now it's under review as a software engineering conference. Or do they understand? So I agree, we're not doing adversarial, but not because we don't care. It's just natural drift is already an open problem. So we want to tackle that, and then we can move on something else. A good question. I believe eventually we should be looking at all of this together. And the question is also quite interesting because you might find that answers that you might highlight tensions. So you might find that you're perhaps very good at natural drift, but still suffering a lot from adversarial. And then the question is adversarial a real problem for your domain for that specific model? Because you're assuming that an adversarial point reaches the model somehow. There's a lot of research now in expanding our reasoning, not just to look at models, but how the model are part of a system, right? Yeah. Conclusion.
Few questions of community in general. So do you see the research community in academia moving away from I have 99% at one score and like adding more to the limitations of the example and stuff like that?
Yeah, I believe so. So I believe we had another work in 2019 that we published at Usenix, where and it was again specific to a problem space, in a specific problem space, where until now people were mostly doing hateful cross-validation. Which is fine, you have to do it, it's okay, but it's not representative of real world. So you deploy, and then once you deploy, you have drift. I mean, if you don't have drift in your domain settings, then K-fold cross-validation is an approximation to what you will observe, like, in distribution over time. That's fine. But the problem is that you don't in our domain. So all the 99 F1 score, they went down very bad. So, but the question is now not the fact that they went down, because of course, they go down. The question is how quickly would they go down? Because if you have something that resists for a couple of months, that's actually great. And then, of course, you need to do some, rejection, active learning, online learning, domain adaptation with unsupervised. There's a bunch of things you can do. But the question is, how quickly does it go down? Because you have a very high performance in distribution, but then the next day the model drops. That's bad, right? So those are interesting questions. No, and I guess, we published that work in 2019, and since then there's been a real shift into trying to reason about temporal evaluation for sure.
Yeah. Then the second question is, I guess, more industry focused, like the all the cybersecurity giants and endpoint response companies, do they use this kind of grounded?
Oh, very interesting.
Theory?
Very interesting questions. So my first answer is I don't really know. And second of all, I don't know. So we've had several conversations with the usual suspect, right? Google, we have a very good relationship with Google. Huawei, we have a good relationship with Huawei as well. CrowdStrike. So we actually just before this talk, I was in a call with some folks at CrowdStrike. So because we're working on something for LLM and reverse engineering. It's unclear. So I guess that the gist is they don't care. Meaning that if I have something cheap that is also interpretable, and I can deal with that. So when we spoke with Google many years ago now, and the Android security team, I mean, they just train as frequently as they can, retrain as frequently as they can. Which is not optimal. You just throw more resources at the problem. It's not optimal, but the point is it's not optimal, not just because, green pollution. Yeah. No, it's also not optimal because it requires labels. Sometimes labels, you don't have labels. There are studies that show that labels are noisy and stabilize only after a year time. So there's a lot of downside in doing that. So the more we are with something that is tighter in terms of semantics, the better it is. The problem is that also you need to account for costs. How much does it cost? So I believe that there will be, so these things will be explored and a bit further when we start having clear evidence that this works. So until maybe a few years ago, there was not much work in active learning and continual learning in our own community. Machine learning is just full of it, right? So now we're starting to reason about this, not just having, so that works that I mentioned, temporal invariance, of course, the learns representation are a bit more stable over time, so then you don't have to update. Great, but eventually you'll need to update. The question is, can you defer updates for as long as possible, maintaining certain performance? Because if you can, that's great, because labeling is costly. It's not about telling you whether this is a cat or a dog. It's not telling you whether something is good or bad, is malicious piece of software or not. It requires a certain level of expertise. So I guess to answer your question, we're getting there. But of course, many of these companies, they don't disclose. And the system, usually there's no one system, it's hierarchy of systems.
Hi, Lorenzo. Thank you for the nice talk. When you're speaking about using problem space examples and feature space examples for adversarial training, I feel that was isolated to sort of adversarial robustness with one perspective. But what about if we wanted certified robustness and we wanted to say that, say you have some boundary around this problem space example, does that cover you well with respect to other problem space examples, or is that definition only in the feature space?
Very good question. Would you like to explore it? I don't know the answer, but it makes sense. Yeah, absolutely makes sense. No, I believe there's a ton of stuff that we need to do that haven't been done.
Yeah, because if you find like a point right in the middle of, say, a problem space cluster, does that mean you look at you take care, you knock out most of the other problem space ones, or?
In principle, yes.
But we don't know.
We don't
Yeah.
know if at least you tackle the one that you should be caring about.
Yeah.
Right. Whether the representation is robust or not is a different story.
Yeah.
Because I can have, from a real adversarial example, I can have still very brittle representation or representation are tighter in a sense. Doesn't matter.
It's like last thing. Can you explain the using of the phrase like tightness and brittleness? How does that go?
Yeah. Yeah. Or maybe no. Yeah, it's about intuition. So because we don't know really. Like, so the point is that, so for me, take driving for instance.
Yeah.
I have this manually engineered feature space where each dimension represents an API that might be in a program or not. Again, it's more complex than that, but let's assume that. Now I can change the behavior of the program in so many ways without altering too much that feature vector. So the actual intent of the program can change a lot without me changing too much the feature vector. So for me, that is brittle because changes in the semantics are not reflected in evidence changes in the feature space representation. Whereas a tight representation to me is something that's connected to semantics. So if I change a key behavior here, it changes also in the feature representation. So in that sense, you're changing it. So you can say, oh, but at the point I can push it in the benign region. Sure, you can put whatever number you want to put it there, but you're changing the corresponding behavior if you want to have now a realistic example. So that's tight and brittle to me. So, and in fact, I have in one slide in some talk, I even trying to conceptualize this in the, I guess my attempt was called the quadrant of confusion, where you try to map semantics and brittleness across axes and then try to map representations in some of these quadrants, depending on the properties that this representation captured. It's a conceptual representation because it's very disconnect from a proper formalization.
If I was an attacker and I tried to not worry about adding a perturbation that causes the semantics to be preserved, and I sort of, for example, just don't care about semantics and just hide some instructions in the binary to convert, like instruction from all of the steps that I need.
Yeah.
Will that get through this system?
Yeah. So in fact, the silence attack, the one that I mentioned in real life, was about this. Like, I guess that they added a bunch of bytes, appended bytes at the end of the binary, so that actually they don't affect semantics. But the model, I guess, was a convolutional network-based model. Their approach to both say, oh, we don't have to engineer anything. Give me a binary and I learn representation. Of course, you learn representation. CNNs are designed to learn the properties of images and create translation invariance representation. What does it mean on software? We don't know, and that's the result. So you can add a bunch of stuff, which is not problem space preserving functionalities, but it doesn't matter. So if you have a brittle model, it doesn't matter. So the point is that we should be moving into something that's a bit more semantic, or again, probably we'll never be able to get to this platonic ideal of semantics. That's fine, but tightening the knot about that, so do you want me to? So tighten the knot a bit more so that you get as close as possible, at least with respect to some of your properties you care about. I didn't have time to explain this, but see here we use code symmetries to learn semantics. So let me just give you the gist if I can. So we published this ICML 2024 as a fairly dense piece of work because the first half is quite theoretical, and then we express everything as the group theoretical perspective, but then we go down to real experiments. So the idea is we wanted to learn some properties for us that were interesting. So they were related to instruction reordering. So sometimes you can reorder instruction without changing semantics. How can you realize this? Well, you build a program dependency graph. I see that there's no dependency use true instructions. I can swap them without changing semantics. Now, if you don't capture this property, and you have this in many parts of the program, you end up by having different representations for essentially semantically equivalent piece of code. So we wanted to have equivariant representation with respect to these properties. The way that we do it, we build a program dependency graph, which is already an approximation. So it inherits a bunch of approximation, but we construct a program dependency graph. From that one, we learn a distance matrix where it encodes how nodes are distant. And those that are not dependent have a maximum distance, infinite distance. And those that are dependent it depends on how many hops they are away. And then we embed this matrix as an inductive bias in the self-attention head of the transformer. Essentially, it tells the transformer, don't pay attention to this part because you can swap it without changing semantics. If you pay attention, then you hinge on some spurious correlation. Okay. So at that point, you end up by having representation that if the only transformation you have is the only symmetry, that's the transformation you have, are this structural ordering, you effectively have the same embedding. Not the same because it's equivariant, so it's close enough. But if you try to plot this with t-SNE or something, you see that there's no violation because by design, you don't need data. There's no data augmentation. By design, you capture this property. Now, the cool part is that that's a very simple property. How about more complex properties? What are the other properties? We don't even know. How about other models? I don't know. There are many things I don't know. More things I don't know than things I don't know. Yes.
Two questions. One very simple one and one more fundamental one.
Oh boy.
The first one is easy. Why is still everybody using the F1 score, not something like the Matthews correlation?
They do also use it. Depends on the task. So for vulnerability, I believe there is a lot of or binary function similarities. Well, instead of the MCC, they use at least recall it, whatever. Yeah, I know because you need. So it's a bit more nuanced and complex than that. So in principle, you should be looking at ROC curve or PR curve if you have class imbalance. But then eventually you want to say, okay, this gives me a picture, but then I want to see how things will work when I deploy it. So you also want to fix something and deploy it. No, it's true. So some of these things, they work similarly to MCC to some extent. Not exactly, not exactly, but similarly. Yeah. I believe it's a community heritage. I guess in software engineering, there's more MCC.
No, not yet. I mean,
yes. Okay, so
constantly
push it, man, push it.
Usage of F1 score in particular for very imbalanced data sets where.
Yeah, exactly. So that's a mess. We have a paper in Usings 2022. It's called Do's and Don'ts of Machine Learning Computer Security, where we try to align some of these things that are quite obvious, but yeah, we keep on making the same mistakes. So we're trying to, it's a form of education for ourselves as well. And we make these mistakes as well because don't pay attention and then.
Amazing. And the second one is more fundamental, philosophical. And that goes back to LLMs.
Yes.
Isn't the most fundamental problem of LLMs the non-separation of data and program? Because prompts are executable. And that's data.
You're talking now about security of LLMs.
No, not just.
Speak about prompt protection.
Also trustworthiness, because
for LLMs, like for the LLM.
For LLMs, how they are used.
Oh yeah, that's a problem. There is a work, I guess it's called Camel. That's tried to look at the problem from information flow perspective and tries to enforce policies to identify code and data in that context, so that provide protection against some of these injection attacks. I guess it's DeepMind and Oxford. So Ilya Shmailov is one of the author. They have a startup now. It's called Security with a Q, security.ai, that tries to work along this line. Yeah, but there's also, so I was in a Dutch Field seminar in November on LLM security and privacy, and there was some interesting theoretical results that shows on the impossibility of providing or showing that you don't have a prompt injection. So, sorry, the impossibility of guaranteeing protection, full protection against prompt injection attacks.
So, should we more look at a clear separation in LLMs for data and prompts.
Probably. How would that affect the reasoning capabilities? I don't know. In fact, it's interesting because there is now evidence also, I guess this was a work by Martin Vetchels at ETH, where they show on the Maths Olympic Games that even though when the LLM gives the right answer, most of the times the reasoning steps are wrong. It's interesting because it opens up interesting avenues for adversarial attacks on LLMs, not just on the initial prompt to induce a wrong output, but maybe to induce wrong reasonings. Why would you care about that? Because at the end, you might have a human in the loop that would actually ask for a reasoning trace to understand whether the output is correct. Or you can think about this in agentic settings where the LLMs produces the output reasoning so that the agents can take decisions, right? So in fact, we are starting looking at UQ, like a certain quantification for LLM, not just for the output, but also we're interested in the reasoning step. We wanted to say, look, these are the reasoning steps. I don't know if it's correct or not, but I'm uncertain about this. So then what you do is, we don't know. Like that's separate. We don't even know how to do that in the first place, but there's a bunch of stuff that we're trying to find out. Thanks.
Thank you very much.
Thank you, guys.